Okay, today we're going to cover all of chapter 1 of your Cambridge textbook, which is on functions and relations. Let's get into it. Okay, so first we're going to talk about sets. Okay, so we've got a bunch of sets here, and sets are just a group of objects that we call elements. So each one, like each of these numbers in the whole set, is an element in that set. Okay, so we've got 4 sets here. Okay. Okay, so the first thing we want to look at is what's called a subset. So we could say in this case that B is a subset of A because all the elements of set B are also in set A. Okay, so we use this symbol to represent a subset. Okay, so everything in B is contained in A, therefore it's a subset. Okay, now what about intersection? So if we want to look at 2 sets and look at the intersection between 2 sets, so we're going to look at the intersection of A and C. So which ones do they have in common? So that's going to be a new set. So we're just looking for the ones that are in common for both A and C. Now C has 1, 3, 5, 7, 9. So it has all the odd numbers up to 9. So in common we've got 1, 3 and 5. So that's a new set that represents the intersection of both of these sets. Okay. Okay, likewise we've got the union. Okay, so if we want to look at A union C, okay, so union just means we're going to look at a set that has all the things in A and all the things in C. Okay, so if it's in A or if it's in C, then it's in this set. Okay, so we've got all the numbers up to 6. 1, 2, 3, 4, 5, 6. Then we've also got, in addition to that, we've got a 7 and a 9. So that is the union of those 2 sets. Okay. Now, if we've got this set D, if we tried to do the intersection of A and D, okay, if we tried to do that intersection, well, they've got nothing in common here. So if they've got no elements in common, then we get the empty set. Okay, and we draw the empty set like that. Okay, and one last one. If we wanted what's called the set difference, so I always call it excluding. So if we wanted to look at A excluding B, or the set difference is everything in A minus whatever's in B. Okay, so that will be a new set. What's in B? We've got 3, 4 and 5. So everything in A, 1, 2, 3, 4, 5, 6. But we're going to take away everything that's in B. So we're going to take away the 3, going to take away the 4, going to take away the 5. So we're just going to be left with 1, 2 and 6. That gives us everything there. Okay, to make this a bit quicker, I have changed boards here. Okay. Now we're going to look at the sets of numbers. So I've tried to pre-write this out for you. So we use the letter N, this big letter N, to represent the natural numbers. And the natural numbers are just 1, 2, 3, 4, 5, 6, all the positive whole numbers. Okay, now they go on to infinity. That's why we don't generally write it out like this, because you could keep going forever. So we just use the letter N to represent that set. Okay, and the letter Z to represent the integers. Now the integers are everything in these natural numbers, the 1, 2, 3, 4, 5, but it also includes 0 and all the negative numbers. So this natural numbers did not have the 0 in it, so it's important to remember that. And I remember the Z represents integers by saying zintegers. Okay, so if you just put a Z in front of there, you'll remember that the z represents all the integers. Okay, so the negative numbers, 0, and the positive numbers. The letter Q here represents the rational numbers. Now the rational numbers now include the integers. Everything in the integers is included in the rational numbers, but it also includes all your fractions, your half, your 3/4, your 5 halves. Every number you can write as a fraction is included in the rational numbers. Okay, then we've got the capital R represents the real numbers. Now that includes all the rationals, so everything in this set, but it also includes what we call irrational numbers. So numbers like pi, we can't write that as a fraction, but it's still included in the real numbers. √2, can't write that as a fraction either. Phi, people might have heard of phi, it's about 1.6-ish, but again has that the decimal numbers that don't repeat in any order, and the number e. Okay, so all those numbers plus an infinite number more are represented in R. So anything on the number line is R. Okay, but we've got these little subsets of R. So R plus, are the reals greater than 0? Now remember, it doesn't include 0, the plus. So again, another case of not including 0. And R minus is, all of x less than 0. So just the negative numbers, but again, not including 0. Okay. Another way to write these, so instead of writing in set notation like this in the curly brackets, we can write in the interval notation. Now, if I give an example, we could have the interval from 2 to 5. Now that interval is everything up to 2 but not including it. Okay, so not including 2 and then everything up to 5 and including that number. So if we were to write that in set notation, that would look like this. X such that, now I probably didn't explain that well before this. So the way we write these sets, X such that X is less than 0. Okay, that's how we read these. So this set, X such that X is between 2 and 5. Now notice how I've got the less than or equal to sign because we've got the square bracket here, and the circular bracket is without the equal sign here. Okay, let's just try one more. So when we're using infinity, okay, so I might do an interval from negative infinity to 1. Now, whenever we've got an infinity at the boundary here, we never go including because we don't consider infinity as a particular number itself. So we always use a open bracket for infinity, and we can write that as X such that X is less than 1. Okay, so that's that. Now we can draw these intervals down here. I don't know if you can see that. Hopefully you can see that on the camera. So this first interval from 2 to 5, so I'll draw that up here. Now to draw that interval, I'll use an open circle because we're not going to include it. 2 to 5 with a closed circle on the end because we're including the 5 but not including the 2. And then for the negative infinity to 1, not including 1, so I might do that in black. So again, an open circle on the 1, and because we're going all the way to negative infinity, we just draw it off to the end of the scale and put an arrow. Okay. All right, change boards. Okay, so now we're up to ordered pairs. Okay, so an ordered pair is just like this. We've got a X and a Y, if you like, and enclosed in a bracket. Okay, so we call a relation is the set of ordered pairs. Okay, so any set that we've got ordered pairs in, so here's our set notation for S. We've got 4 ordered pairs, and that's what we call a relation. So anything that we can express like that is a relation. Now the domain is just the set of the first values in each ordered pair. So we could write the domain, we can call the domain X if we like. So that set is going to be 1, 2, 4, and that's it. Because we've got 4 twice. And then the range, I should do this in a different color, is just the second number in the ordered pair. So for this, we've got 1, 3, 8, and 9. There we go. So that was really easy. Relation by rule. Often we don't have just a set like this. We're given a rule for the set. So here we've got T, so for the ordered pairs X and Y, such that the Y follows this rule for X. Okay, so Y is equal to X squared minus 1. Okay, and for our X values, our domain here is X is an element of the real. So this is given our domain in the rule for the set. So we can write that in. We could write it in this notation, or we could just write it in this notation. X is an element of R. Okay, and our range, the Y values here. So let's have a look at what we get. I'll just graph this. So for X is an element of R, X squared minus 1. We've got a parabola that is, hopefully that looks okay. Just move down one spot. So an X squared minus 1, move down one spot. So the Y values, everything from here, this is -1 there, all the way up to infinity. So these are the values that Y can take. Y never takes any values down below -1. We've got the minimum here. Okay, so Y is greater than -1. We could write that. Okay, we could also write it in interval notation. We could write from -infinity to infinity. That's the same thing. Or we could write from -infinity to -1. Oh, I've made a little mistake here because the -1 is included. Okay, so I need to have included of -1 there, and this becomes a square bracket. So that's really important to make sure you're getting that right. Okay, next slide. We've got functions. Now we're getting into the real stuff. A function is a relation that for each x value there is only one corresponding y value. Okay, so what does that mean? A relation is a function if it passes the vertical line test. This is the easy way to figure out if something is a function or not. Okay, so let's even just take this function here. Okay, y equals x squared plus 1. Well, this relation, and we'll see if it's a function. So we drew it before. It's a parabola that's been moved down 1. Now the vertical line test means, can I draw any vertical line? So any vertical line, and it only ever touches the graph once. So it only cuts the graph once. Any vertical line I can draw. If I can draw one vertical line that cuts it twice, then it's no longer a function. It must be a relation, but this one is definitely a function. So if I was to write this in what's called function notation, so I'm going to write this in function notation. So the way I write that is I write function f such that, okay, I'll write in blue. Okay, such that, now we write the domain first. So the domain is R, okay, which maps to what we call the codomain. Now in mathematical methods, this is always going to be R, okay? So it's saying that the range is a subset of this codomain, okay? So this number here is the domain, which I got from here, okay? I know what it is. This is the codomain. And And we know it's not the range. It's just saying that the range will be a subset of this. Okay. All right, so we've got R maps to R. Function of x is equal to x squared minus 1. Okay, so this is the same thing. This is our set notation. Well, it's a relation, so it's an ordered pairs in set notation, and this is our function notation. Okay, let's do an example. You can restrict the domain. You can have a different domain. Doesn't have to be R. So let's have G. So is 2 to 3. Close bracket. Maps to R. Now remember, the codomain is always going to be written as R in mathematical methods. Okay. Now we've got G of x is equal to 5 minus x. Okay, and if we graph that, we're going to have an open circle at 2. So that's 2, and what do we get when we put in 2? We get 3, and it's going to go down, get a closed circle there at 3, 2. So I go towards 3, that's a closed circle. What do I get when I put in 3? 5 minus 3 is 2. Okay. All right, next board. One-to-one functions. All right, a function is one-to-one if it passes the horizontal line test. So let's have a look. Here's my function, R x squared minus 1. This is got to be close to one of my favorite functions. Used it a lot already. Now, does it pass the vertical line test? Well, we've already done that. We've tested every line. It only cuts once. So yes, it must be a function. If it passes the vertical line test, it's a function. Is it a one-to-one function? A one-to-one function will mean it passes the horizontal line test. So the horizontal line test, will it cut once for any horizontal line? Ooh, no. Okay, cut the graph twice for that horizontal line, so it didn't pass. That means it's not a one-to-one function. Okay, now let's have a look at this function g. Now this function is a different function to this, even though the rule is the same. It is got a different domain. Now the domain is very important for defining a function. So if I say that the domain is only from 0 to infinity, then this is a different function. So let's go from 0 to infinity. So 0 inclusive, closed circle. So I only get that positive half of the function. Now does it pass the vertical line test? Yes, it does. Only cuts once. Horizontal line test? Well, it's only ever going to cut once, isn't it? Okay. So now this is a one-to-one function. G is a one-to-one function, but F is... Okay, implied domain, or the maximum domain. Okay, so for this to be a function, okay, f of x equals the square root of x minus 3. What is the maximum domain we can have, the largest domain that will still make this a valid function? Okay, so we've got a square root sign. We've got to remember that we can't square root negative numbers. We can square root 0, that's fine, but we can't square root negative numbers. So we don't want anything under this to get less than 0. So if I had x equals 1, that'd be 1 minus 3, which is negative 2, so that's not allowed. So I need numbers that are bigger than 3 for this to be greater than 0. Okay, so I've got x greater than or equal to 3, because it's allowed to be 0, so that's fine. So that's my maximum domain, or my implied domain. Okay, what about this one? Now we know there's a rule about fractions. We can't have the denominator being 0. So this is this factor multiplied by this factor. So if one of these factors is 0, then it's no good. But all the other values are fine, as long as it's not 0. So it can be negative, just can't be 0. So I can have x is an element of R, but I want to exclude 2, because if I exclude 2, 2 minus 2 is 0. So I want to exclude 2. And I also want to exclude -1 plus 1 is 0. So I want to exclude -1. Okay, and they're my maximum domains. Okay, a piecewise function or a hybrid function, it's just when you have two rules that make up a function and they're different over their domain. So as long as the domains don't overlap, then this is fine. So I want a domain here. Let's go for a domain. Oh, it doesn't even matter. Let's just go everything, all the negative numbers, so x less than 0. So as long as I define the domain, I'm okay. So now I want for including 0 and all the positive numbers for this part. And that'll get me across all the x values. It doesn't have to, but it will in this case. So if I say, I'll do x is an element of R plus, but I also want to include 0. So if I want to include 0, I'll do in union with the set that has 0 in it. Now that's not the empty set, that's just a set with the number 0 in it. There's a difference. Okay, so this has got one element and that element is 0. If there was no elements in the set, then it would be the empty set. Okay. Okay, a few more definitions. An odd function, when you've got f of negative x, gives you the same as when you have the positive value of x, but it's the negative number. So that means you get a rotation around here. Okay, so an example for that sort of function would be y equals x cubed, or f of x equals x cubed. Okay, so this is an odd function. So if you rotate it 180 degrees, you get the same thing. Or the other way you can think of it is you flip that in the x-axis and then reflect it again in the y-axis. Or you can do it the other way around. You can reflect in the y first, reflect in the x, and if it overlaps the function, then it's the same thing. Okay, then it's an odd function. Okay, so an even function, almost the same thing. When you've got negative x, you get the same thing as you get when you put in the positive version of that x. So you've guessed it. I'm guessing y equals x squared. Okay, remember you label your axes for full marks. Okay, so it's just a reflection in the y-axis. If you've got a reflection in the y-axis and it's the same graph, then it's an even function. Okay, so lots of definitions there. Let's move on to the next board. The next board is this one. Sums and products functions, sums and product functions. Okay, so let's consider these graphs. Let's firstly, for these functions, what are the maximum domains for these functions, or the implied domains? So we just did that. So this one, x can take any value, it doesn't matter. So we've got x is an element of R. What about this one? As long as x, right, this doesn't become negative, so it has to be greater than -2. Okay, so I don't want under the square root bracket to be a negative number. So x is an element of, I'm going to write interval notation this time. I'm going to write from -2 to infinity, and I'm going to put a circle bracket. Okay, so anything greater than -2, I could have just written x greater than -2 or equal to -2, that's fine. Okay, so let's consider a sum function. So the sum, this h of x is going to be the sum of these two functions. So we'll write that down. So this is going to be f of x plus g of x. Okay, so what does that look like? That's f of x is x squared minus 1 plus x plus 2 in a square root. Okay, so g of x plus f of x. What's the domain of this function? Okay, now let's think about this. Now the domain of this function has to be the domain that is the intersection of these two domains. Okay, so we've got to have it covering both. Okay, so it's the intersection of the domain of f with the domain of g. Now in this case, domain of f covers everything, this doesn't quite cover everything. It covers from -2 to infinity, so the domain for this one is going to be x is, well, I'll write the other way around this time. X is greater than or equal to -2. Okay, so the domain for this has to be the intersection of these two domains. Okay. All right. Let's do a product. Instead of adding them together like we did for the sum, we're going to do a product, which is multiply them together. So f of x multiplied by g of x. So to do that, I'm going to go x squared minus 1 multiplied by, I don't need the bracket there, the square root of x plus 2. So what's the domain of this graph? It's the same. Okay, so as long as we've got a subset, or the intersection of these two individual ones, then it's going to be defined for that domain. Okay, next one. Okay, quick board. Addition of ordinates. Okay, so here we've got the sum of those two functions we had before, x squared minus 1 and x plus 2. So I've drawn out the f of x and the g of x. So this is g of x on its own. I've just penciled them in, well, not penciled, but dotted them out because they're not the actual function I want to draw. I want to actually draw h of x. So what is that going to look like? Well, it's just the sum of these two. So I want to add up the ordinates in a straight line here. So here at x equals -2, the g of x is 0. So if this is 0 at -2, then h of x is just going to equal the same as what this function equals at that point. So if I go straight up there, h of x is going to have this point on it. Okay. Same thing when f of x is 0. So 0, this is 0. And then this bit of the graph is going to be here. Okay, so it's going to lie on g of x. And if I think about the intersection here, I'm going to get double, well, it's going to double the height. So it's going to go add that, well, if that went up to 1 or something, then this is going to go up to 1. So then that's going to go up to 2. So I've got that happening. Okay. So then it's going to come and it's going to turn around. By the time I get to here, it's got to be there. Where it cuts here at 0, it's going to be on the G graph. Okay. And it's, well, this is fading off and this is getting bigger much quickly. So it's much more quickly. So it's going to go up there somewhere. So it's going to look a little bit like this. And then it's going to turn around and go back up in that direction. Okay, so that's what my graph of h of x is going to look like. Now, remember at the end of the graph here, I've got because we know this is only going to be defined for x greater than or equal to -2, so that's the stopping point there, whereas it goes on forever in the other direction. So I've got an arrow there to represent that. Okay, next one. Where am I up to here? Composite functions. I should have a look at my notes. Okay, composite functions. All right, so we want to have a look. We've got this graph again. What's the implied domain? We'll find the domain and the range. Okay, so we're going to look at both. So we know x is an element of R for this one. X can take any value for R. What about the y values? All right, it's a parabola that's moved down -1, so it never gets less than that. So this is y is from -1 to infinity. Okay, or y greater than or equal to -1. Okay, so this one we said x is an element of -2 to infinity. Okay, what happens to the y values? Well, the y values are everything in the positive axis. Never goes below, you never get a negative number there, so it's going to be r plus in union with 0. Okay, now hopefully that makes sense to people. The other way I could have written that is just y is greater than or equal to 0. That's the easiest way to write it, I suppose. This is the cumbersome way, but often happens in methods, so good to be aware of both. Okay, so now we've got the domain and the range of f, and the domain and the range of y. Now that's really important for this, and I'll show you why here. Okay, we're talking about composite functions, so we're going to make a new function h as a composition of these two functions. So we're going to really mold these two functions together. So we're going to put g of x inside of f of x. So I'm going to take this whole function here, and for every x in f of x, so for every x here, I'm going to put the whole function of g of x in place of that x. Okay, so the f of x function, the outside function, it is a something, so the x squared, got the thing squared, minus 1. Okay, so I've put, that's the outside function. The inside function here, g of x, is the square root of x plus 2. Okay, so now, if you think of this, this is like x squared here, minus 1. And for every x, instead of having x here that is squared, I'll put the whole function g of x in. There we go. Okay, so what does that equal? What does that look like? All right, if you square a square root, they sort of cancel out. So I get x plus 2 minus 1. So I just get x plus 1. Okay, now we've got to have a look at the domain of that function. So now this is a bit tricky to think about. Okay, so when the x values come in, we've got all the domain of g of x can go, this is my conveyor belt system. Okay, so this is a conveyor belt. Okay, so I've got inputs and outputs, and this is my g of x machine and my f of x machine. So I've got g of x coming in. Okay, so they can take any x values that g of x can take. So that's all the domain here. So we're going to have anything from -2 to infinity coming in. What's coming out is the range of g of x, so that's y greater than 0. So that means these are going to become the new inputs for f of x, okay, because g of x was inside, yeah? G of x is inside f of x, so the new domain for f of x is the range of g of x, okay? So the domain, luckily, the domain for f of x is R, so we can take any values. As long as it's a subset, okay, as long as the range of g of x is a subset of the domain of f, okay, then the composite function is going to work, okay? So these values go in, and we get the range out, okay, so whatever that range may be. Okay, so this is going to work because the domain of f of x is R in this case, yeah? Domain of f is R, so because this is encompassing, you know, this doesn't go outside the boundaries of R, you know, R is our biggest boundary anyway, so that's where we're good to go there, okay? Well, biggest boundary in math methods, okay? So we're fine. So our domain is going to be the same as the domain of g of x here. Okay, so our domain for this h of x function is going to be for x greater than or equal to -2. Okay, same as this. All right, let's have a look at another one. We'll look at it in reverse. What if we get, so this is called f of g, right? Same as this. I didn't explain that before. I should have done that. G of f, okay, goff, fog, goff, okay, goff, g of f, okay, is a g of f of x. Now, f of x is now the inside function, and g of x is now our outside function. So let's do it around the other way. So for every every x in our outside function, I'm going to put it with our inside function. Okay, so I'm going to have the square root of x squared minus 1. Okay, that's my x, and then I've got plus 2 after that. So this is the square root of x squared plus 1. Okay, let's look at if it's defined or not. So we've got to think. Now I want to know if the range of f is a subset of the domain of G. So let's have a look. So the range of f is a subset of the domain of G. Is that true? This is from -1 to infinity, and this is from -2 to infinity. So it fits inside this domain. So we're all good to go. So the domain is now going to be the domain of f. Now the domain of f is R. So this is x is an element of R. Much bigger domain than this one. So that's interesting. All right, but there's an extra complication here. Okay, I'm going to go to a new board. Let's have a look at what happens here. Okay, so what if, just a small change, I've changed this g of x to x minus 2 instead of x plus 2. That's the only difference I've made. Now we're going to look at g of f of x. Okay, so g of f of x, square root, let's do the domain and range. So x is an element of R, and y is greater than or equal to -1. Cool. This one, x has to be bigger than 2. As long as it's bigger than or equal to 2, we're fine. And then y is greater than 0, yeah? Okay, so we're going to get numbers that are bigger than or equal to 0. Okay, so g of f of x is the inside function. It's going to fit inside this outside function. So for every x in this one, I substitute in the whole of the function of x. So I've got x squared minus 1 for that x, minus 2. That gives me x squared minus 3 altogether. Now, does the range of f fit inside or a subset of the domain of G? So let's look at the range of f. The range of f is from -1 to infinity. But okay, the domain of G is smaller than this domain. So it's got values in this one that doesn't fit inside this one. For 0, for example. So the range y equals 0 here, yeah, we can't have 0 in here, so it doesn't work. So that means we're going to fall apart here when we put in values that give us y equals 0 out. We're going to fall apart. This whole thing's not going to work anymore. We're going to get numbers less than, let's have a look what happens. So 0 squared, 0 minus 3, I've got the square root of minus 3. That doesn't work. Okay, so I'm in trouble. So can I then restrict this domain of f of x in order to make sure that the range here will fit inside here? So what I want this range to be greater than or equal to 2, so then it fits inside here. So what do I have to change this domain to in order to get that to happen? So what I do is I draw my graph of f of x, the inside function. So draw it out. And I look at the range from -1 to infinity. Now I want the range to be greater than or equal to 2. So if I draw that, there's my y equals 2 line. I want it to be above that. Yeah, I only want to get these values. So I've got to work out what x values are going to give me numbers, these numbers, the ones that are greater than 2. So I can look at my graph, go x squared minus 1 is equal to 2, my boundary. Yeah, I can solve that equation, move the 1 over to the other side, x equals plus or minus the square root of 3. Okay, so this is root 3 and this is negative root 3. So what I want to do is change it so I get either numbers that are bigger than root 3 or less than negative root 3, and then I'm fine, I'm good to go. So if I change this, now this function, so that x is an element of negative infinity, right, negative infinity to negative root 3, right, I can include that number, that's fine, in union with, right, so that, or I can have positive root 3, right, all the way to positive infinity. I don't have to write the positive, just write infinity. There we go, and circle bracket there. Okay, so I've excluded all these numbers in between because all those numbers are going to give me a y value less than 2, which is no good. It's going to destroy my function here. Okay. Okay, inverse function. So what's an inverse function? Okay, so here's my conveyor belt again. So if I've got x values coming in to the function changes the x values and y's come out. Is there a function where I can put in the y into the function and get x back out? So I want to reverse the procedure to get x back out. Okay, so for inverse functions, the function has to be one-to-one. Okay, and this is because, like, if, for example, if you had a function y equals x squared and you put in 3, so you put in 3 into the x squared function, it would come out as a 9. But then if you wanted to undo that, you might think, oh, just take a square root. But if you take a square root, you could get plus or minus 3. So we've got a bit of confusion there. Which one do I get back out? Do I get back out the plus 3 or the minus 3? So as long as the function is one-to-one, then we don't have that problem. So each individual y value will have an individual x value. Okay. All right. So what happens? So the domain of f, the domain of this one, so the inputs into this one are going to be the range of f. Yeah. And the range, what comes out on this side, we want that to be the domain of this one. Okay. So let's have a look. We'll add a little example. So we've got a function here from r plus. Okay, so that's all the positive real values, not including 0. The codomain of r, x squared minus 1. So let's draw that. So we've done this before. We get this function here. Okay, remember the open circle because it's not including the 0. Okay, we want to find an inverse function for this. So the method we use is we say let y equal the inverse function of x. Okay, and then what we do is we swap the x and y's in this function. If we think of this as y equals that, then we're saying that y is the inverse function. So we're going to put a y in for x. So we're going to say x equals y squared minus 1. And then we're going to solve for y. Okay, so if we solve for y, we're going to move the 1 across. So we're going to get x plus 1 is equal to y squared. I'm just going to rewrite this around the other way and go, therefore, y equals plus or minus the square root of x plus 1. Hopefully you can still see that. So which one do I take? Do I take the plus 1 or the minus 1? Now we want all our range here, yeah? So we want the domain of this to be the range of this. So we've got the range being from -1 all the way to infinity. So we want the domain of this one to be from -1 all the way to infinity. And we're going to get just the positive versions here. Okay, so we'll write this as y equals positive square root of x plus 1, since we want all our x's to be greater. No, hang on. Since we want all our y's to be, oh, hang on. No, sorry, I'm getting confused here by looking at this graph. So we want all our x's to be greater than -1. Okay. So another way to think about this is, since we're swapping the x and y's over, all of our points on here are going to swap the x and y value. So here we've got the y value of -1. Okay, so they're going to swap their x and y values. Okay, so we get this reflection in the graph of y equals x. So whatever you get here, you get reflected on this side. A couple more definitions. Okay, some more definitions here. Okay, strictly increasing function. Okay, it's just a definition. If b is greater than a, that means f of b has to be greater than a. Okay, so strictly increasing. Let's draw a strictly increasing graph. So the easiest one to draw is f of x equals x cubed. Okay, strictly increasing function. So for any value, as you go further up here, it doesn't matter if you compare a b and an a value, so you might take a as being here and b as being here. Okay, so when you put that into the function, f of b is going to be higher up the ladder than f of a. Okay, it doesn't matter what values of a and b, as long as b is bigger than a. Okay, strictly decreasing function, you might have guessed it, exactly the same. B is greater than a means f of b is less than f of a. So you could get a graph that does that. I have not drawn that well. Okay, so you might have f of x is equal to -x squared plus 5. Okay, this is a strictly decreasing function for the domain, so we should have put that in there. Oh, I'm going to run out of room. Let's just put it over here. It's not the best notation, but you get that. Okay. All right. Now this is a busy board, but let's not make it more complicated than it actually is. It's quite an easy one to do. Power functions. Okay, so we've got functions that have a rule x to the power of n. Okay, so I've broken it up into four shapes you have to remember, and these are really easy to remember because this is like a parabola, like f equals x squared. This one's an x cubed, so like a cubic. This one, a truncus, and a hyperbola. And they're the only ones you've got to remember. Okay, so if n is positive, you get these two. So if you get a positive power of n, you get these two graphs. If you get n being negative, you get these two. Okay, you get either the truncus or the hyperbola. Okay, and then if n is an even numerator, if you have an even numerator or a odd numerator, and the reason I'm calling them numerators because you can think of these as fractions, these powers. So this is 2 over 1, 3 over 1, negative 2 over 1, negative 1 over 1. So think of just the top number of the fraction. If that's an even number, then you get the parabola. If it's odd, you get the cubic. And same over here. Even, you get the truncus shape. Odd, you get the hyperbola. Okay. Now, there's a couple of little two little rules you've got to remember on top of that to get various other shapes. Okay, so if n is between 0 and 1, okay, so that only includes these positive ones. So in these two sections, so between 0 and 1, it's still positive. Okay, we need to flip the concavity of the curve. Okay, so if you have, for example, like 0.5, or if you think of that as 1/2, then you need to flip the concavity. Okay, so that means changing, so instead of being concave up, you change it to concave down. So it's going to go like that. Okay, so we'll do an example in a minute. I'll give you another example. Okay, another rule is if the denominator is even, then you cut off the first quadrant. Okay, you only use the first quadrant. Okay, so you cut off the second quadrant. Okay, and that's really it. Okay, so, and that includes these ones as well. If the denominator is even, you cut off that first quadrant. Okay, they're the only two rules. So let's give an example. Let's do f of x equal to x to the power of 3/5. Okay, so we've got a number between 0 and 1 here, so we want to flip the concavity. Okay, and the denominator isn't odd, the denominator is is odd, sorry, it's not even. So we want to go to, we've got a odd numerator, so we're looking at this one, okay, but we just need to flip the concavity. So instead of going up like this, it's going to go concave down like that. Okay, again, like this, flip the concavity, and you get that. Okay, so that's going to be the shape. It's still going to go through 0, 0, 1, 1, negative 1, negative 1. Okay, let's do another one. If okay, so one more, so you get the idea. F of x equals x to the power of let's go 3/8. Okay, so 3/8. So I'm mainly focusing on these ones because the other ones are quite simple to do. So I've got 3/8 now. It's between 0 and 1. 3/8 is less than 1, but more than 0. So we're going to flip the concavity again. The denominator is even, so we're only going to take that first quadrant. Okay, so here we go. We've got an odd numerator, so we're taking this shape here, and we've got an even, so I'm going to take that. So we've got to flip the concavity and only take the even number, and that's it. How easy is that? Okay, let me just try and get, can you get something cool? Let me just do one more, just to get the idea, because that was a bit easy. Let's get this one, like fx equals to x to the power of 2/3. Okay, so for this one, we've got, again, between 0 and 1, so we're going to flip that concavity, and we've got an even numerator, right? The denominator is odd, so we don't have to worry about this one. So now we're going to get this shape, even numerator, and flip the concavity, so it's going to go back the other way. So we're going to get this happening, which is kind of cool, I think. All right, so that's really it for fractional powers. You use those shapes these rules and you've got the answer. Okay. Last board. That's excellent. Okay. All right, last one. Here's an application. We've got a rectangle inscribed in a circle of radius A. Find the area of the rectangle function. Okay, so we want the area of this. Okay, so where do we start? So we want to relate the rectangle to this radius A. We want to use that piece of information. So if I start at the center, how do I go to the edge of the circle and still be touching the rectangle? Well, the only place to do that is in the corners. So I can pick a corner. All right. So we've got this. This is length A. Okay. So we could split this up into a right angled triangle like this. Okay. So let's call the sideways horizontal movement X and the vertical Y. Okay. So how can we relate these things, the radius and Y and X? We've got a triangle here, so we're going to have to use, and it's a right angle triangle, so let's use Pythagoras' theorem. Okay, so we've got Y must be equal to, this one has to be equal to the square root, this one squared minus this one squared. Yeah, this is, A is the hypotenuse here, yeah? So we'll go A squared minus X squared. So there's our relationship between Y and X. Okay, now we want to find the area of the rectangle. So what do we know about the area? Well, we could draw the same thing on this side, and that gives us the width of the rectangle. So how much is the, draw the same thing there. And so our height is going to be 2y, and our width is going to be 2x. So the area of our rectangle, length times width. So our length is 2x times our width, 2y, or whichever way you want to call it, doesn't really matter. So I get 2 times 2 is 4, 4xy. Okay, and this is great because we've got a value for y here in terms of x, so we could substitute that in. So I get 4x square root of a squared minus x squared. Okay, so this is the rule. We've got the rule now. We've got the rule for our area, but we want to write it as a function, so we've got to have the domain. Now, how big can x get? Right, so for different rectangles in here, the maximum x could be is 2a. Yeah, it couldn't be any more than the diameter of the circle. Okay, so we're going to write this in function notation. A such that a is between 0 and, x is between 0 and 2a. That's going to map to r. We get the rule a of x is equal to 4x square root of a squared minus x squared. That's it. Done. Okay, there's a simple application for you.